So this last lecture in our first unit on kinematics for the grade 11 physics course is about projectile motion. This is another very important topic in physics. You will come across this again if you take the grade 12 course. You'll see it again if you go on to university to study physics. We are going to look at what are considered kind of simpler projectile motion problems in the grade 11 course than the grade 12. However, that isn't to say this is an easy topic, but I will go through it, and hopefully with the homework practice and the use of our class discussion board, you'll be able to learn this topic as well. So first, what is a projectile? A projectile is anything that really moves under the influence of gravity to kind of have what we call projectile motion. Here we see a picture of a dirt biker kind of jumping through the air, and if you notice that motion, it does kind of look like a parabola, which makes sense because we learned when we were looking at position time graphs that when we have a parabolic position time graph, we have uniform acceleration, and when you're accelerating due to the Earth's gravitational field on the Earth's surface like we do, we would be having uniform acceleration due to gravity. And that's where projectile motion is kind of analyzed under. We usually look at it at Earth, or on Earth rather. Our motion is governed by the constant g, or well, it's not really a constant, but it's we round it to an average of 9.8 meters per second squared. And that is how we study projectile motion. So here are the definitions of a projectile and the definition for projectile motion. A projectile is any object that moves in a two-dimensional curved trajectory. It's a parabola in response to gravity. Projectile motion is the motion of a projectile under gravity. So here, let's look at a situation where we have two balls, and one of them is dropped, whereas one of them is kind of given a horizontal velocity. Which one would hit the ground first? So this is a stop motion picture image of a red ball being dropped and a yellow ball being given an initial velocity to the right. You'll notice that at different times they are at the same height. The horizontal acceleration, or sorry, the horizontal velocity of an object is independent of its vertical acceleration. So what I basically just said is that both objects will fall at the same acceleration, regardless of what their initial velocity is in the horizontal direction. Some things that we use to define projectile motion are range and time of flight. So time of flight is the time it takes for the projectile to hit the ground, or rather the time it's been in the air until it hits the ground. Range is horizontal range more accurately. So it is how far it moves in the horizontal as it goes through its projectile motion. So write down the definition for time of flight. It is the amount of time it takes for a projectile to complete its motion, which is usually when it hits the ground. Range is the horizontal distance traveled by a projectile. So if you came from a math class, you might be thinking range is the domain. Domain is the x and range is your y values that you could be. Here we're talking about horizontal range. It's the horizontal distance traveled by a projectile. Just make sure you note the difference. So now we're talking about projectile motion, but some of these concepts can be used for other types of two-dimensional motion. Let's think of a situation where somebody lives at a home and their school is across a river. That's what we have here. The river itself could have a current that will push you to the left, to the right, up or down, or I guess I should say north, south, east, or west. But your motion across the river might be in a strictly north or south direction. So you might be going north or south to go across the river, whereas the river is also pushing you east or west. So these are some things to consider. The same idea with projectile motion. You might be throwing an object horizontally, but it's going to be pushed down by the acceleration of gravity. So here, back to this problem with the boat going across the river. Let's say that a person traveling from the school back home tries to go directly north. The current will push them towards the east in this case. So they'll end up not at their home, but at some landing point that is to the east of their home. So this example is another example where we have this independent motion. The motion of the water is independent of the motion of the boat. So you can be moving your boat north. The water can be moving you to the east. Both the velocity vector that you push the boat north and the velocity vector that the water pushes you east would have to be added together to determine a resultant velocity. So in a projectile motion problem, let's say we're throwing a ball out a window. You would give a ball a horizontal velocity. It is going to experience a vertical acceleration going down. So it might have an initial velocity in the vertical direction of 0, but when it hits the ground, it's going to have a non-zero velocity vector for its vertical velocity. So in this picture, you see the projectile's motion. The Vx is the same at all points in the position of the ball as it's being thrown. The Vy gets greater as we get closer to the ground because the Vy is accelerating, whereas the Vx is not accelerating. So said differently, your vertical motion is non-uniform and your horizontal motion is uniform. And that's what this slide summarizes. Horizontally, the motion is uniform, A equals 0. Whereas vertically, it's non-uniform, A is equal to g, which is 9.8 meters per second squared. So to solve problems involving horizontal direction, we would just use the equation V equals d over t. To solve problems in the vertical direction, we would have to use one of the 5 equations of motion. Now, even though these motions are independent of each other, they have one factor that's common, and that factor is time. So I kind of gave it away a little bit there. Time is the same. So if it takes 10 seconds for something to fall, it also had it experienced that horizontal velocity for 10 seconds. So we can use that idea to find the range once we find out what the time of fall is, or the time of flight. So to solve these types of problems, these projectile motion problems, we assume that acceleration is due to gravity and that it's constant and that the direction of gravity is down. We assume that there is no air resistance either. In more complicated courses, or you might see air resistance being taken into account, but that won't happen in your high school career. So this is a very important slide to copy down for projectile motion. To solve these problems, first to note that they are two-dimensional. There's horizontal and vertical motions to consider. We have, when we're looking at the horizontal x-axis motion, it's uniform. A equals 0, so we use V equals dx over tx. The vertical motion, we have an acceleration due to gravity of 9.8 meters per second squared down. We can use those 5 uniform acceleration formulas. Time is common for both. So the time of flight is the same. And there's the two assumptions we make. G is constant, air resistance is negligible. Launching a projectile horizontally. This is the situation I gave where we throw a ball horizontally. This is one type of projectile motion problem you'll have. In this case, it's best to take down as positive and right as positive if we're throwing something to the right. We'll do a sample problem like this, but just before we do, I'll just explain simply. This is considered the easiest type of projectile motion problem. Basically, once we find how long it takes something to fall, we can then find its range of motion. So let's look at this problem. Okay, so in this question here, we have a beanbag being thrown out a window. The initial velocity is given to us as 3.0 meters per second. That's our Vx rather than Vi. We have the dy that it travels is 10.0 meters. So that is our height. We need to find, in this question, how long it takes this beanbag to hit the ground. So what we're really looking at is we have our acceleration in the y direction. We have our distance traveled in the y direction, and the beanbag doesn't have an initial y direction, or rather its initial y direction is 0 meters per second. So what we're really doing here is we're trying to solve for t given dy, ay, and vyi. So using our equations of motion, the original 5 equations of motion, which I'll bring up here for reference again, we have a d, an a, and a vi, and we need to find a t. So I look at this equation here, and I can solve that. That is d equals vi t plus 0.5 at squared. And in this case, it's dy equals vit becomes 0 because that's not, vi is 0. 0.5 g t squared. And I'm trying to solve for my t, so this becomes 2 dy over g, and I square root that. Because I'm taking down as positive, this is a positive and that's a positive. So I have the square root of 2 10.0 over 9.8. Let's calculate that. So 2 times 10 divided by 9.8, and I find the square root. I get 1.43, or I'll say 1.4 seconds. The next part of this problem, though, says how far horizontally does this beanbag travel? Well, to solve for part B, I'm going to need to consider that I rounded this value here. Even though this is the solution here to the proper significant digits, which we'll talk about before we start Unit 2, I still have to consider all of those values you see on the calculator up there. I have to consider all of those values when I find my dx. Even though it might still be the same if I used this, I still have to consider those. So to find this distance, remember we're using the Vx equals dx over t equation. And I'm just trying to solve for dx, which is my range. So it's Vxt. And dx equals v, which is 3.0. My t, I'm just going to write in 2 extra decimal places, so 4.29 would be good. But I will calculate, sorry, you don't see it there. I'm going to calculate using this exact value I have still in my calculator. Multiply that by 3.0. And I get 4.28, or dx equals 4.3 meters. Now in this case, it worked out to being the same if I would have used 1.4, because 1.4 times 3, oops, 1.4 times 1.4, 1.4 times 3, actually it doesn't, it would have been 4.2. So that's a reason why we have to use the exact value. That way we consider all of those trailing decimal values that we did not consider when we rounded it. But we have to round it to our significant digit values. Okay, now that's one type of problem. Here is another type of problem. Here it says a hockey puck, or actually this is the same type of problem, but just without the picture. A hockey puck is launched horizontally from a roof that's 32 meters tall with a velocity of 8.6. So we're asked to find what's the time of flight, and I'll just go back to find out what's the range. So time of flight and range for the hockey puck. Let's turn this on and figure this out. So time of flight, we know the, let's see, we'll go with this. Givens are dy. We know the viy is 0. We know the a, which is g, or ay, and we know the vix. So we have to find time of flight. This is the same as the other type of question. dy equals viyt plus 0.5 ayt squared. I've already sort of solved this, rearranged it. It's 2 dy over g. So t equals the square root of 32 over g, which is 9.8. Let's see what we get here on our calculator. 2 times 32 divided by 9.8 square root is 2.6. But I'm going to keep that value in my calculator because I need to find out what my distance traveled in is. So dx equals vxt. Dx would be vx, which is given us as 8.6, times 2.556. But I'll use the exact value. So I write down 2.556, but I use the exact value when calculating. I end up with a dx of 22 meters. So those are the simpler type of projectile motion problems. There is one that is a bit more difficult to do that we'll look at. But before we get there, let's talk about, oh actually sorry, we're going to skip this. This was something that we were doing but is not conducive to an e-learning environment, so you can skip those lecture slides. The next type of problem we're going to look at is when we launch a projectile and it lands at a spot at the same height. So not being thrown from a building. This is our type 2 projectile motion problem. This is when we're throwing something in the air and it lands at somewhere at the same height. In this case, you're given both initial vertical and horizontal components. Your vertical velocity ends up becoming 0 when you reach your maximum height, and then it ends up speeding up again due to the acceleration of gravity, and it is a non-zero value, the vertical component, when it hits the ground. The entire time of flight, though, your horizontal component is the same value. So here's a question where we have a soccer ball being kicked. So it is a soccer ball that's being kicked 9.4 meters per second at an angle of 40 degrees. The horizontal and vertical components can be found by multiplying the initial velocity, the 9.4, by cosine of 40 and sine of 40. But we'll get into that when we get to the problem itself. So let's first look at the time of flight for this problem. So we have a number of equations that are used to simplify this. So I'm going to come back to this really soon. I thought the lecture showed them first, but I think it's better if we go through those first. So let's go here. These are the equations that show up on your formula sheet that can be used to simplify these types of problems. So range, maximum height, and time of flight. Each of these equations, the v that you're given is the v of is the initial velocity regardless of the angle. So it's the magnitude of the velocity. And then your angle is used in different formats to solve your range, your maximum height, and your time of flight. So we're going to use these equations to solve each of these questions up here for 8. So first what we'll do is we'll figure out what equation to use for each one. Time of flight is the first one. So the time of flight equation, that is over here. So for 8b, we're trying to find the time of flight, so that's t equals 2v sine theta over g. Let's do 8c. 8c was the question where we're asked the range and then the height. So the range for 8c is our horizontal range equals v squared sine 2 theta over g. That's sine of twice theta. And then 8d is the maximum height. So h subscript max equals v sine theta squared over 2g. So all of these, we can solve each of these. Let's go back to the problem. So from the problem, we know that we have a v of 9.4, an angle of 40. So t equals 2 times 9.4 sine of 40 degrees over 9.8. Here we have r equals 9.4 squared sine of 2 times 40 degrees over 9.8. And here we have our h max equals 9.4 sine of 40 squared over 2 times 9.8. So for each of these problems, we'll turn the calculator on and solve. 2 times 9.8 times sine of 40 divided by 9.8 is 1.2 seconds. The next one, 9.4 times 9.4, because it's 9.4 squared, times, this is going to be sine of 80, because 2 times 40 is 80. And then I have to divide this by 9.8. My range is 8.9 meters. My h max, 9.4 times sine of 40. This value is squared, and again divided by 2 and divided by 9.8. H max is 1.9 meters. So the last thing to do here, there is another type of problem. I'm just going to mention this, but you will not see this in this course. This is the most complex type of projectile motion problem. It's when you launch something into the air and it falls at a height that is not the same as the height from which it was launched. These involve solving quadratic equations, which you may or may not have done yet in math, but you will see this in grade 12. So you don't have to worry about it for this course.